Okay, so in our sequence of videos on thermochemistry, the next one we're going to go over is molar enthalpy change. Enthalpy is represented by the variable H, and then of course the triangle there representing delta, it signifies change. So enthalpy is the flow of energy or exchange of heat at constant pressure when two systems are in contact. So it's the transfer of energy from one thing to another. There are multiple different types of enthalpy. We have enthalpy of reactions, combustion, formation, fusion, vaporization. All of those things are different types of enthalpy. But the important thing is, regardless of type, the unit is kilojoules per mole. More formally, we would say kilojoules per mole reaction. In terms of my specific class, as long as you have kilojoules per mole, we're doing good. Having the reaction there is definitely something more that's appropriate for AP chemistry. We can calculate enthalpy from several sources: stoichiometry, calorimetry, from tables of standard values, Hess's law, and from bond energy. But it is only stoichiometry, calorimetry, and Hess's law that we cover in pre-AP Chem. The table of standard values and the bond energy piece is something that is saved for AP chemistry. So today we're going to focus on the stoichiometry version of enthalpy, and we'll get the calorimetry version in our next video. So our formula here is going to be delta H is equal to the moles of the substance times the heat term over the coefficient. And it's important to know that the moles of the substance and the coefficient used have to be for the same substance from the balanced equation. Okay. We can come up with one of two types of answers here. We could come up with a negative delta H value, which signifies that this is an exothermic reaction, that heat is being released in the reaction. Or we can come up with an endothermic value, a positive delta H value that shows that heat is being absorbed in the reaction. Okay? And all of that is going to be determined by the information garnered from the heat term. So let us look at our first example. What is the molar enthalpy change if 17.54 grams of sulfur reacts with oxygen to produce sulfur trioxide? And then we're given an equation that includes an energy unit. So let me stop for just a second, explain some things that are going on in this equation. So in this equation, I have 2 moles of sulfur and 3 moles of oxygen combining to make 2 moles of sulfur trioxide. And that combination is going to release, I know this is released because my heat term here is on the product side, so it's exothermic, 741 kilojoules of energy. But this amount of energy comes from the entire reaction of 2 moles and 3 moles making 2 moles. In molar enthalpy, I want to break that down and determine not only what would be appropriate for 1 mole, but what's appropriate for the amount of substance that I have. So we're going to run through kind of how stepwise we figure this out. So first thing is, let's look at our balanced equation. So again, we said that this is on the product side, and because it's on the product side, I know that this is going to be heat release. So product side, therefore this is exothermic. And when I write this in isolation outside of my equation, it would have a negative value because that is showing that it is being released. So negative 741 kilojoules. So my equation again is moles times this heat term. Well, currently I don't have moles, I have grams. So I need to convert my grams to moles, which is going to be done through stoichiometry, which we already know how to do. So 17.54 grams of sulfur times 1 mole of sulfur over the molar mass of sulfur, which is 32.07 grams of sulfur. So if I just look at this real quick by itself, 17 is a little bit less than half a little bit more than half the molar mass of sulfur. So I'm really dealing with just over half a mole when I'm calculating. So that's going to get me grams cancel. It's going to get me moles. Now I need to multiply by the heat term. The heat term is negative 741.4 kilojoules over the coefficient from the balanced equation. So these moles are for sulfur, so I need to use the coefficient for sulfur over 2. So when I put this into the calculator, 17.54 times negative 741.4 divided by 32.07 times 2. And that's going to come out to be negative 202.746. So, first of all, I knew that this was for the entire reaction. So dividing it by 2 gets down for 1 mole of sulfur, how much energy 1 mole of sulfur would be. And then this part of our equation takes into account that I don't necessarily have 1 mole of sulfur. In this case, I had just a little bit more than half a mole of sulfur. So per mole, per what we have, it's going to be, let's see, check our sig figs, 4 here and 4 here. Those are the only 2 places where my sig figs can come from. So 1, 2, 3, 4, negative 202.7 kilojoules per mole, and if it's negative, exothermic. And you can just write exo or endo is fine. So a full answer is going to have a number with it's either negative or positive sign based on whether it's a negative or positive value, and an endo exo. Okay? Make sure that if it's negative, you have a negative sign, and if it's positive, you do have a positive sign. In my class in particular, you will lose points if you don't have a positive sign. Okay? I want to see that you are explicitly stating that this is a positive value if it is one. All right, so let's look at our next example. In our next example, how much molar heat will be transferred when 53.81 grams of carbon reacts with hydrogen to produce C6H6? And we're given a balanced equation. So let's break down again what we're seeing in this balanced equation. So my heat term this time is on the reactant side. That's showing me that this is going into my reaction. It's a reactant. Therefore, this is endothermic. And my value is going to be positive 149.03 kilojoules. Okay? So this much heat is required to get my 6 moles of carbon and my 3 moles of hydrogen to react and form C6H6, which is benzene. So in my problem, I have 53.81 grams. And so we're going to run through and see how much this is going to produce. So delta H is equal to 53.81 grams of carbon times 1 mole of carbon over 12.01 grams of carbon times my heat term, positive 149.03 kilojoules is what was produced, but that came from 6 moles. So that means per mole, it's a lot less than that. All right, so math, let me scoot this up a little bit for you. 53.81 times 149.03 divided by 12.01 times 6. All right, positive, make sure you have the positive sign, 111.2864. All right, and then we'll check our sig figs. So here I have 5. Here I have 4. I can only keep 4. So 1, 2, 3. This 8's going to round over. So positive 111.3 kilojoules per mole endothermic. Okay. All right. And let's look at our last one. When 1 mole of methane is burned at constant pressure, 890 kilojoules per mole of energy is released as heat. Calculate the delta H when 5.8 grams of methane are burned. Well, what's different here? Oh, there's not a balanced equation. Well, the way that this question is worded actually means that you don't need that. It's giving you all the information that you would need in a balanced equation in the first sentence. When 1 mole of methane is burned at constant pressure, 890 kilojoules of mole per energy is released. So it's telling me the heat term is 890 kilojoules per mole, and it's telling me that the coefficient is 1. And because it's telling me that it is released, I know that it's negative because this is exothermic, because I have this word released. So this is another way you could see this type of problem. Most often you'll see it with the balanced equation, but I do want you to be able to recognize it this way as well. So delta H is equal to 5.8 grams of methane. Well, methane is CH4 times 1 mole CH4 over, and then we need the molar mass of methane, which is 16.042 grams CH4, times my heat term, which we said was negative 890 kilojoules because it was released per 1 mole, or 1 as our coefficient, equals. So let's see. 5.8 times negative 890 divided by 16.042. Oh, I didn't need that parenthesis because it's times 1. Oh well. So negative 321.78. And let's check out our sig figs. 5.8 is 2. 890 is 2 because there's no decimal. So 1, 2. This is going to be negative 320 kilojoules per mole. And if it's negative, we know it is exothermic. Okay. All right, so we're going to stop here, and then I'm going to start a second video on enthalpy diagrams. Enthalpy diagrams is just a way to visually interpret what we've just done here to look at the difference between reactants and products. So I'll be right back.